Picture this. Your organization just invested millions in cutting-edge AI infrastructure. The latest GPUs, specialized computing clusters, and lightning-fast storage. But 3 months in, you discover that these expensive resources are sitting idle 40% of the time. Even worse, your developers are waiting days to get their AI workloads scheduled, while critical models are taking ages to deploy. This scenario is playing out across industries as organizations rush to implement AI without the automation foundation that's needed to make it efficient. The stakes? Wasted investment, delayed innovation, and of course, competitive disadvantage. Well, I'm looking at the 2025 Priorities Report from Worldwide Technology, and Priority 3 stands out: automate in support of AI implementation. It highlights that unlike traditional workloads, AI implementations require specialized infrastructure that's extremely costly when underutilized. Today, I'm joined by Corey Wanless, a principal solutions architect who's been helping organizations automate their infrastructure for over a decade. Corey brings real-world experience in DevOps principles and container platforms, making him the perfect guide through this challenging landscape. Welcome, I'm Rob Boyd, and this is WWT Presents Research.
WWT Presents Research.
Well, Corey, hey, thanks so much for joining us in this research episode. We're talking AI, specifically Priority 3. But first, do you mind reminding us, because actually I think it's changed, what is your current title with Worldwide Technology?
I am a principal solutions architect here in our Advanced Technology Center.
Very good. Well, congratulations on that. I think that was within the last year or so.
Yes, thank you.
But we've worked together before on similar shows and other technology topics. Today, we're talking about Priority 3, which is about automation in support of AI. And so around this principle, around the automation priorities, this particular one, there's a statement in here that talks about how, well, AI workloads are different and that it's fundamentally important to understand why they're different and what kind of effect, I guess, that can have on your infrastructure. Do you mind explaining what these differences are that are important to understand so we can get into why we need to deal with them?
Yeah, so the main thing that I like to focus on are there's two aspects of things I like to look at. One is how you use the equipment or the gear, the physical infrastructure. And the other aspect is the physical infrastructure itself is different. We're so used to whenever we're running out of capacity of compute, we just add another node. And whatever the solutions that we're fitting into, whether that's a virtualization solution or some bare metal solution, those have some known scalability configurations. The difference in the AI is, yes, we can scale by adding nodes, but those nodes are significantly more expensive, somewhere on the power of 10x, as well as they require a lot more power and cooling, which they have to take into consideration when you're talking with your facilities teams and whatnot, and making sure you have the right ample power and cooling to support that added workload. So you don't want to go through a cycle where you're just adding for the sake of adding because you know you can scale it. You want to make sure you can consuming that physical infrastructure in a way that is optimizing the consumption versus just adding because we have the budget for it today or whatnot.
Yeah, because that budget won't stay because these things are ridiculously expensive. So you're talking about the expense to acquire as well as the expense to operate. Are people building new data centers for this kind of thing, for those that are at least doing their own models?
So there's two different types of workloads within AI that I like to put everything into as far as buckets are concerned. One is the inferencing side. This is the day-to-day consumption of a model. So when we think about the Llama 4s of the world or Llama 3s, DeepSeek, those already pre-trained models that we can run within your GPU infrastructure, that's inferencing. So you're building applications that are calling that model that exists, that's running in GPUs and getting the results back from that. The second is the training. The training is where you're actually building the model. So that's where Meta and their team is building the next Llama, if you will.
The hyperscalers.
Exactly. Additionally, those companies that are like building things like DeepSeek, there's plenty of others that are building smaller, large language models, but that's a different way of operating your GPU infrastructure. It's different because training is more of a batch workload. You try to consume as many GPUs for as long as you can. As soon as your training is done, you want to give that back to the environment to use or for the next training job to run. Whereas inferencing, there's not really an end state for that inferencing workload. It's going to continue on until you move on to the next model that you want to deploy as these applications are consuming that model day in and day out for your users.
Just to make sure that I'm picturing this correctly, because on one hand, a couple of breakdowns to understand, I think as we call them frontier models when we access ChatGPT, some of these other publicly available models that give us a chat box into it. Maybe we're using the API and interface, but those are ones obviously built by hyperscalers. These are built at massive scale. There's some version of this that enterprise organizations are building themselves and playing with to say, is this where our next competitive advantage is going to come from? And that's really where we're focused here, correct? Which is doing these models yourself in-house, perhaps both inference and training, or training then inference. But it sounds like you could use a model that's been pre-trained by someone else.
Yes.
No.
And when we talk about leveraging an existing model and wanting to do further fine tuning of that model, it is called fine tuning. I just answered my own question. So
I love the way that works.
yeah. So there are processes in which you can actually take an existing model and run it through a training job to actually further fine tune it for your given use case. And there's a number of different technology stacks that enable that capability. But that is also kind of in that training box. It's just typically with fine tuning, you generally have less GPUs you're consuming and you're more targeted in what you're trying to do, meaning that model in the end state is going to be answering more targeted questions for your users versus a broad basic questions like a traditional Llama 4 would, right?
And I assume IT departments in a given, say, a large organization, perhaps could have multiple training things going on with different groups. So you are looking at subdividing GPUs for certain tasks at a certain point in time. And then as those training jobs finish and or other things are available for inference, they want to be able to move GPUs between different uses.
So there are different technology stacks that enable customers to be able to queue up jobs. So the kind of keyword there is being able to queue up workloads in order for, one job that's training against maybe 20 of your GPUs. But there's another job that comes up from another team, but there's not enough GPUs at that time to satisfy the need. So it gets queued and then it runs at the point in which the other job completes. Different technology stacks within that allow that to kind of happen. And what we're seeing a lot of nowadays is a lot further alignment into one stack, which is known as Kubernetes. Kubernetes is a containerization solution that we see that's been out in the market for a very long time, originally created from Google engineers, but is the main, or at least the main driving force that I've seen from customers and from some of our partners around how they build their solutions to help accelerate AI outcomes.
Well, let me ask you, because we're going to get into Kubernetes in just a moment because it's part of our action steps. And so we will come back to that because I do have some questions. Automation is key, as you're saying, to the optimization of GPUs, no matter what the resource is. This is not something you want to be doing manually, I guess, is what we're also promoting here.
Yes, exactly.
Okay.
GPUs are going to be the most finite resource you have within your IT infrastructure. It happens with us within the ATC. Everybody asks for, hey, I want to have access to this GPU or that GPU, or I need 20 of these or 10 of these. We get those asks every day, and we have to help prioritize where we provide the right access in the right way. And so the same happens with our own customers. They have thousands of use cases and maybe hundreds, if they're lucky, of GPUs. And when you look at it from that scaling perspective, you have to prioritize what efforts you put into AI so that you can actually leverage all of the GPUs and not just try to string along as many projects as possible with very, very finite capabilities.
Well, and hopefully you're watching this or have made considerations like this prior to investing in those GPUs, because the clock, I would think, is ticking when you have to pay for them and when they're sitting there being used or not used. Boy, you better have a plan. And so let's get into the action steps. You mentioned Kubernetes, which is the very first action step, is build a Kubernetes foundation. Let me do the other ones before we go back to that, though. The second action step is to optimize GPU utilization. You've talked about how important that is, but we're going to talk about why automation is fitting in there. And then automate AI testing as the third. But going back to Kubernetes foundation, I feel like Kubernetes has a reputation that, at least for some people, that might recoil a bit, be a little bit that causes some brakes to be put on. Is that fair to Kubernetes? And is Kubernetes the only way to go about doing this?
Yeah, I believe that if you look at Kubernetes in just the open source ecosystem and have never dove into what's the capabilities of the product and overall kind of ecosystem of tools and products that fit into Kubernetes, it can feel very daunting.
I get that. Yeah.
And so what I generally recommend to customers is to really look at certain OEM partners that try to package, or they do package up their own supported delivery mechanism for Kubernetes and supporting technologies around it. And so when you look at those and you pay for that support, not only will you get something that you know is going to be reliable, it's going to have documentation around their best practices and how things are integrated with each other, rather than trying to go all open source and look at every single tool that's out there, especially in the AI space, where it's so new. There's about 20 tools for one use case in Kubernetes for anything around AI today, because it's just, everything's developing so quickly that people are building, open source projects that are solving the same problem in 20 different areas. And which one do you choose now?
Well, this is why I come to you guys, because it is confusing. But that's a great point, because I remember when I was preparing years ago to do some Kubernetes talks with probably some other engineers, I believe it was at Worldwide, and I was just, oh my gosh, it's a whole different language when you start going down this route of all the tools and everything. But it very much makes sense to me, because there's a lot of things in our life where, I just installed a new TV in this home that I bought, and it's got, I think it's an Android operating system in the background. But I don't have to interact with Android. So if you said, well, you need Android to use this TV, and I'm like, I'm not an Android guy, I'm an iOS guy. It doesn't matter, because I'm not interacting with that. I'm interacting with the vendor's interface of this, and it's simplified, it's focused. So you're saying those things are prepackaged, they make some decisions for me. Why did Kubernetes kind of emerge as a de facto standard for doing this automation around? Why do we suggest it for the foundation here?
Yeah, so I believe it all stems from the actual open source community. The open source community is one driving a lot of the AI outcomes as we see it, right? Even Meta open sourced their model. And a number of other companies are choosing to do more of an open source kind of go to market for their product line, because it gets more people involved to develop and mature their own product.
Because we need speed on this stuff. It's all moving so fast, I guess, that, yeah.
Exactly. The talent's not there. It's sparse in different places. So being able to use open source technology to accelerate and bring people together to solve certain specific problems is needed within the AI space. And that's why it kind of bubbled up. And when you look at the open source community around the infrastructure side of things, a lot of solutions are building on top of Kubernetes as the foundation, because they know it's a stable solution to help run a distributed workload across a very large number of compute nodes, including ones with GPUs.
Because what you're talking about with Kubernetes is no one has the ability, like a singular company, to say, we've decided it needs to operate in this fashion and mess up all your previous work. You don't have that issue perhaps with Kubernetes, because number two is optimized GPU utilization. And so I think some of the stuff you're talking about, NVIDIA is to be praised for the amount of work. They have plenty of money. The work that they put in, not just to the GPUs, but the surrounding technologies that make these GPUs useful. They're very focused as they should, but they do control some of those things. So we're going to have to build in a NVIDIA based direction, I would assume, for this optimization as part of step two. But where does, I'm just easing right into this next one. Where does automation affect GPU utilization? How do those two interact?
I look at Kubernetes itself before diving into more of the GPU side of it. Kubernetes itself is the automation for infrastructure.
Okay.
There's tooling that goes around Kubernetes to help get things into it and running on top of it. But Kubernetes by itself is a declarative way in which to manage your infrastructure, as well as the applications that sit on top of it. And so when we look at the GPU side of it, NVIDIA has built this operator called the NVIDIA GPU operator, cleverly named. Its job is that when you install it inside the cluster, it's going to look at all the nodes that are in your Kubernetes cluster, figure out which ones have GPUs, and then start tagging each node for what GPUs are on it, how many GPUs are on it, and the different hardware aspects as it is related to that node. So when we look at a Kubernetes environment and architecting it for a customer's kind of outcome, for how they want to consume those GPUs. We look at how can we allocate a quota of resources to a project or use case and prioritize that project so that when a workload comes in, it runs on the right nodes at the right time for the right amount of time too, for them to get their needs met. So if it's for training, there's going to be a small point in time that they need those GPUs. If it's inferencing, we know it's going to be a longer period of time, months, years, if not longer, for them to consume that set of GPUs or be able to migrate from one set of nodes to another set of nodes. As it relates to kind of Kubernetes, when we're looking at the consumption, the optimization of consuming those GPUs, there's a lot of Kubernetes elements that are declared for us on how to keep an application HA inside of the cluster, as well as migrate workloads from one node to the other. There's a lot of concepts about draining nodes so that if you need to upgrade the cluster, you can drain in node by node by node, and allow that cluster to upgrade without providing end user impact to any potential downtime.
So it's kind of invisibly happening behind the scenes on behalf of the users. And this is the automation that is taking these declarative states, understanding when things begin, when things end, and making sure that, I assume, we minimize the amount of time that a GPU is not doing something useful and applying itself.
Correct. So our time is spent less writing automation to say, build thing 1, then build thing 2, then build thing 3. Our automation now is focused on build all 3 things and let Kubernetes and our underlying configurations decide when to run it and how long to run it.
Oh, yeah. Okay. That makes sense because you've got this level of deep visibility and control, and it's set up, obviously, so the machine's making the decisions because by the time we make the decision, we're wasting resources left and right. Well, one question I've had, because I think this has changed, that hasn't there been, it's funny because it feels like the history is not that long, but hadn't it been that we, at one point in time, it was all GPU or nothing. So a singular GPU is either tasked with something, but now you've got fractional GPU. So there's more optimization decisions to be made, which probably also says this is another reason why automation becomes important. Is that true?
100%. It is absolutely important. And it's important for each organization to make decisions on how they want to do fractioning, or if they want to do it based off of whatever their workload requirements are. And so there's a number of different ways to do that. So out of the gate with NVIDIA, if you're running like an A100, H100, and some of the GPU models, you have what's called MIG, which is a way in which to fractionalize at more of a hardware level. So think of it like partitioning of GPUs. Like if you think about a hard drive and setting it partitions, it's very similar in how MIG works from NVIDIA, and that's out of the box. And you can configure that method of fractionalization. Usually the drawback we see with customers is MIG is very static. In order to make a change, you're most likely going to have to get workloads off that box, reboot the box for it to come into that configuration. It's more like a hardware-based partitioning. And then you have the next option out of the box from NVIDIA is time slicing. Time slicing.
Timeshare. I want to buy a NVIDIA timeshare.
Essentially what you're doing is you're saying, I want 2 containers that don't know about each other to talk to the same GPU. The benefit of that is if you have a lot of known small models, but are using large GPUs, you can fit a lot of these small models on a single GPU. But the problem is these 2 containers running different isolated workloads don't know about each other. They can start to have, the bad neighbor effect where one person is one container is getting a lot of work going on. Maybe there's a lot of requests going on. Maybe it's that time of the year. It's getting overwhelmed and it's making the other suffer. And so you could see within that use case, that one has its limitations, has its benefits, but also has its limitations. And so then we see that NVIDIA made an acquisition in RunAI. RunAI has its own way of doing GPU fractionalization, more at a software level, which is a lot more flexible than the other existing options. So it kind of bridges the gap between the hardware partitioning and just, give everything one GPU and cross our fingers. And where it fits is that you can actually assign it a percentage of a GPU, and it will then offer that percentage to a running container. And the container, when you look at the configuration it's been given, it looks as if it just got that small fraction. And so then all the processes that are running on it,
It's going to make decisions based on that.
exactly. So it's all running within that, which then again helps from a resource availability perspective, and things of that nature. Additionally, with Run AI, since we're on the topic of their solution, is they build a custom scheduler into Kubernetes. So Kubernetes has a scheduler. That's the component that says, when I need to run a container, where do I run it within the cluster, right? Do I run on this node, that node, the other node? They have their own custom scheduler that enables even more efficient scheduling of workloads. So if you have a lot of small jobs, what it does is what's called bin packing. And so it moves all those small jobs to running on one node, which then frees up other nodes to take on the larger jobs. So you may have a handful of really small models running on one node with Run AI, and Run AI chooses to schedule the larger, maybe the 405 billion parameter models on the larger boxes so that it can be saved for those larger workloads. Because out of the box, the Kubernetes default configurations are generally just going to be which node responds with availability the quickest. So you can have more of a fragmented configuration.
There's not a big picture understanding of what needs to happen globally, where the priorities are maybe being considered, and when things are ending, I guess, too. Is there a little bit of an understanding that, hey, this is going to free up and these now make that available at this point in time for these, and let's do that efficiently?
Yeah, everything's kind of built in underneath the hood for how they do that. And you can even do larger, there's other concepts within Run AI that help with scheduling, which is like node pooling. So let's say you have an HR department that decided to invest in the infrastructure, and you in your organization says these 3 nodes are for HR. You can use node pooling from within Run AI to actually make sure that the only jobs scheduled on those nodes are ever from their projects.
So this is funny. I feel like we went from step 1 with Kubernetes. I'm like, woo, Kubernetes. And you made me feel better about Kubernetes, because I'm like, okay, no, the pre-packaging, that makes sense, right? We know we have a need. We know what we're aiming for. That helps a lot. So some decisions are made. But now we get into step 2, and we talk about optimizing the GPU. This sounds like there's a lot of very unique decisions being made about the trade-offs of certain decisions. If you're using scheduling a certain way, if you're doing your fractional GPU a certain way. And so those probably, I would assume, are not as prepackaged, because they're going to involve unique trade-off decisions, assuming they're even aware of what the trade-offs involved are. How obvious, beyond the obvious, which is use you guys to help make those decisions, I would assume there's not an easy answer for understanding your trade-offs until you've been working in this for a while.
I would say the answer is still developing. If I want to
It's fair.
give an answer now, I would say it's relatively complex space for choosing how you do fractionalization, if you do fractionalization, so on and so forth. And then what solutions sit on top of Kubernetes that you want to use. It's still relatively a complicated and evolving market. If you ask me this question 6 months from now, I probably will have a different answer, just like anything from an AI perspective. That's why I love this work we do within AI space, is that it's so new. The things I did last week are old news, right? The things I'm doing this week, I'm preparing for it to be old news next week, right? And so it's a fun but exhausting but rewarding space to be in.
I was just awarded an advanced degree in prompt engineering, and I thought that was going to pave my way forever. And now I'm finding out that maybe that's not as important. Just kidding. Prompting is still very important.
Yeah, I was going to say
it's such a minor user thing. Yeah,
it's what you'll find if you as you dive into the AI space is prompt engineering is not just the surface level. It's also what goes on underneath the hood. We don't know. The public doesn't know exactly what ChatGPT does behind the covers. When it goes off and does its discernment for your answer, we don't know how many prompt changes happen on the back end to make sure it's not doing anything harmful back to you, that you're not trying to trick it, and things of that nature. Those are closed source, methods that they're not providing to
well, there's methods and some that they know, but then I remember reading some of these papers from Anthropic where they're running tests which is a segue into step 3, which is automate your AI testing. I feel like you set me up beautifully for this segue. But I remember reading about these tests where they're discovering, oh, turns out it does recheck an answer here. And it wasn't that they had built it in, it's the system acting relatively organically, certainly not sentient, as some people, got booed for claiming. But boy, it sure feels interesting, and how smart these things get. But let's jump right into testing. Why is testing important in this domain?
Yeah, testing is really important for the AI space, more so than your traditional application.
Okay.
When we're dealing with a traditional application, we're dealing with an application that has very known inputs and outputs. It's very deterministic. We know that if I put in 1 + 1 and ask the system to solve that for me, it should come out 2. You ask some of the original LLMs, what's 1 + 1? Sometimes it might come back as 3. And so the difference between a deterministic application and a non-deterministic application is the fact that within a deterministic application, there's a lot of backend changes that can happen that won't affect the outcome of that application. Using LLMs that produce non-deterministic results, meaning 1 + 1 may not always equal 2. You have to build your applications in a way that one will deal with error checking of responses from LLMs that are not correct or perceived as potentially correct, and deal with that logic, that retry. But then also means that you have to test differently too. What we see within customer bases is if they don't do testing, one of the hardest things to do is actually go from one model to another model, or the latest release of a said model, because they got so comfortable with the response of the LLM and the structure of that LLM. So let's take an example. There's a lot of use cases where people use LLMs to construct a SQL query. User asks question, okay, LLM, here's how my database schema looks. Please formulate a SQL query that would answer this person's question based off the schema I provided. And then it will provide you a SQL query to then run from the application against the SQL database. Take that simple example. It may work well on an older model. You tested it, you made some changes to your prompt engineering to get it to work. And then your IT solution providers, hey, we're trying to get rid of that old model. Can you please move to the latest, greatest model? That the cycle of the things in which you integrated into the LLM need to be retested vigorously. What are all the user permutations of the input of asking questions that you're expecting a certain result back out of? Working through building testing frameworks so that every time you promote or push code up to your Git repo, it's testing against all those permutations, but also so that your operations team, when they want to move from one model to the other, they have the same testing framework that they can call upon to test against the new model.
Am I correct in making this inference in that in the deterministic side that you speak of, one example might be you got the Apple operating system. My application written for this version of the operating system works great, tests great. I release it. Now Apple updates the OS. I've got to retest and make sure that nothing has been broken. Now that's one thing that is challenging to keep up with, and there's investments in those resources. Is that the same type of thing here? Is that you develop things based on the model, but it needs to be easy to test consistently so that you know exactly where things are off, since it's not deterministic. It's not going to be a mathematical change. Oh, they changed these things in the model, so I know exactly how that's going to change my application. You don't know until you test, it sounds like, correct?
Exactly. You don't really know the difference.
Because it always gives you a response.
It always gives you something. Is it consistently giving you the right response, right? And sometimes with prompt engineering, it is about tuning the prompt to give you a consistent result, because sometimes it's just not consistent. One query will work, the next one doesn't. So one shot test doesn't always mean that you're good to go. Let's move on. Whereas with more of an OS upgrade, the OS is going to respond the same way every time that you make a system call from your application down to the Apple operating system, for example. That's the case with LLMs. So you can hit it on a bad day where it just wants to give you an attitude, and you have to deal with that error checking. And so the testing part is both to improve the resiliency of your application and how it deals with potentially bad responses, as well as the operationalization operationalizing onto new models and moving on so that you can safely, take back some of the GPUs you're consuming, right? If you're assuming you're using more of an on-prem approach or where you're actually managing GPU. So it's a way of saving costs on that side too.
Well, that's interesting too. Yeah, because I guess that has to be part of the testing since you can't really predict in advance what kind of load certain things are going to put on it. And as we learn more, testing allows you to optimize potentially for that, especially if you've got a life cycle, I guess, where you're moving, hey, we've done a training, but we want our inferencing. Maybe our training's happening at a hyperscaler, but then we're bringing it in-house for inferencing or vice versa. I don't know.
Yeah.
Different cost models.
100%. You're hitting on
Okay.
a whole other area of testing, which is making sure, especially if you're hosting your own model, you're creating a baseline for what is the performance of this model on this infrastructure. It's very important to say that all of these configurations are exactly how we want to deploy them in quote production, meaning that the model and the GPU type and the number of GPUs that you throw at that said model are going to be what you're going to go into production with, and then test against that. What is the performance of that model from that? What is the tokens per second? When's the response time of just the first token versus all of the tokens? And then how many concurrent requests can I make to the inference server and things of that nature? So they have a baseline. The whole point is to create a baseline of, at best effort, how much can this one deployment of this model handle? And then from there, you extrapolate, okay, but we expect this type of workload, and let's go ahead and scale that by 5 because we need to be able to meet that performance workload by scaling.
Yeah, it sounds like the ability for the test to be consistent, because that's the only way to really work from a baseline, because everything is so inconsistent on the model side. That's the way you're going to, so we have a new model. It's better. It's faster. Trust me. Don't know till we run tests against it. And those tests have to be identical to the tests we ran before. Otherwise we don't have a apples to apples comparison to make and to say, and to, of course, see how things break, I guess. All 3 steps, very broad, build on a Kubernetes foundation. That suddenly appears like the simplest one now in hindsight. Optimize GPU utilization and then automate AI testing. Lots of little decisions and things to make in between there. But just in case we've lost anybody in this conversation, executives watching this and trying to make decisions about the importance of automation and making sure that is reflected in their investments when it comes to their AI, dreams, hopes and dreams, making sure that the right stuff is included to make sure that they're going to get the results that they really want out of this. It sounds like automation sounds pretty important for this, but what's the one thing you'd want people to remember?
I think you just hit on it. Automation is key when managing your AI infrastructure, as well as how that it gets exposed up to your app developers. Without automation, you are guaranteeing yourself to consume more GPU resources than you thought you were going to consume. And being able to pull those resources back after the fact is going to be a lot harder. So while the initial cost of building in the automation to support your AI initiatives might slow you down initially, it's going to accelerate you well beyond the slowdown from your initial need to invest in that area.
So it sounds like if you go into this somewhat manually at first, just trying to minimize or dipping your toe in the water, at some point you should be thinking about how automation is going to do that, because you're not going to be you're going to find something successful, but your ability to scale it efficiently and then make sure you're seeing a return on the investment that matches up with expectations, because the expectations continue to get higher and higher. And our ability to do those things quickly is probably going to make a difference in life or death for certain companies.
Yeah. And expectation is definitely a thing to watch out for within the AI space. One of the key things around automation is making it self-service and making it so that people can try things fast and fail fast. Because there's so many projects that we've seen where, we've been working on this for months and months and our expectation is really high. We're just trying to get through setting up the infrastructure the way we want it to. And they get to actually trying to do the use case and realize it just doesn't work. Making sure you have the right automation in place to accelerate the time to try something out. And even if it's going to fail, at least you're going to learn something from that failure. That's the important thing from this new landscape that we're sitting in today, is that expecting failure is important. But it's how you respond after the failure is even greater importance about how you take that learning and apply it to the next project, right? There's lots of projects that we spun up where it didn't pan out the way we wanted to. And then, 2 months later, we learned something on another project. And we're like, man, I wish we knew about this thing we just learned on the old project, and trying to reapply it to what we tried, and then bring that project back to life, right?
Yeah, gotta make sure that you're getting something from every interaction. Otherwise, truly wasted investment if they're not learning from those failures.
Mm-hmm.
Well, Corey, thank you so much.
I appreciate your time, as always.
Well, as we've explored today, implementing AI without proper automation is like buying a Ferrari without knowing how to drive. Expensive and ultimately frustrating. The 3 steps we've covered, building a Kubernetes foundation, optimizing GPU utilization, and automating AI testing, all provide a practical roadmap for organizations at any stage of their AI journey. What stands out from my conversation with Corey is that while AI technologies might be new, many of the same automation principles remain the same, just with higher stakes and more specialized requirements. To learn more about automating in support of AI and other automation priorities, I encourage you to download the complete 2025 Automation Priorities Report from Worldwide Technology. And if you're ready to take the next step in your automation journey, request an automation briefing. This is where WWT experts can discuss high-impact use cases specific to your organization. I'm Rob Boyd. We'll see you next time.
This episode is supported by Glean. Glean is the work AI platform that connects and understands all your enterprise data to generate trusted answers and automate work grounded in company knowledge. Put AI to work at work.